So you only have to implement one algorithm and you get both algorithms the same way. The only difference is that the functions are applied in reverse order. Okay, so this Feistel mechanism is a general method for building invertible functions from arbitrary functions f1 to fd. And in fact, it's used in many different block ciphers, although interestingly, it's not actually used in AES. So there are many other block ciphers that use a Feistel network. Of course, they differ from DES in the functions f1 to fd, but AES actually uses a completely different type of structure that's actually not a Feistel network. We'll see how AES works in a couple of segments. So now that we know what Feistel networks are, let me mention an important theorem about the theory of Feistel networks that shows why they're a good idea. This theorem is due to Luby and Rockoff back in 1985, and it says the following. Suppose I have a function that is a secure pseudo-random function. Okay, so it's indistinguishable from random and happens to act on n bits. So it maps n bits to n bits and uses a key k. Then it turns out that if you use this function in 3 rounds of a Feistel network, what you end up with is a secure pseudo-random permutation. In other words, what you end up with is an invertible function that's indistinguishable from a truly random invertible function. And I hope you remember that the definition of a secure block cipher is that it needs to be a secure pseudo-random permutation. So what this theorem says is if you start with a secure pseudo-random function, you end up with a secure block cipher. Basically, that's what this says. Now let me explain in a little bit more detail what's actually going on here. So essentially, the PRF is used in every round of the Feistel network. So in other words, here what's actually computed is the PRF using one secret key, K0. Here what's computed is the PRF using a different secret key, of course applied to R1. And here we have yet another secret key, K1 applied, K2 applied to R2. And you notice this is why basically this Feistel construction uses keys in K cubed. In other words, it uses 3 independent keys. So it's very important that the keys are actually independent. So really we need 3 independent keys, and then we end up with a secure pseudo-random permutation. Okay, so that's the theory behind Feistel networks, and now that we understand that, we can actually look at the specifics of DES. So DES is basically a 16-round Feistel network. Okay, so there are functions f1 to f16 that map 32 bits to 32 bits, and as a result, the DES itself acts on 64-bit blocks, 2 times 32. Now the 16 round functions in DES are actually all derived from a single function f just used with different keys. So in fact, these are the different round keys. So ki is a round key, and it's basically derived from the key k, derived from the 56-bit DES key k. Okay, and I'll describe what this function f is in just a minute. But basically, you see that by using 16 different round keys, we get 16 different round functions, and that gives us the Feistel network. So just at a high level, how the DES works, basically you have a 64-bit input. The first thing it does is this initial permutation that just permutes the 64 bits around, namely it maps bit number 1 to bit number 6, bit number 2 to bit number 17, and so on. This is not for security reasons, this is just specified in the standard. Then we go into the 16-round Feistel network that actually you now know how it works. Basically uses the function f1 to f16 as specified before. And then basically we have another permutation. This is called the final permutation. That's just the inverse of the initial permutation. Again, it just permutes bits around. This is not necessary for security reasons. And then we finally get the final outputs. Okay, now as we said, there's a key expansion step, which I'm not going to describe. But basically this 56-bit DES key is expanded into these round keys, where each round key is 48 bits. Okay, so we have 16 48-bit round keys, and they're basically used in the 16 rounds of DES. And then when you want to invert the cipher, all you do is you use these round keys, these 16 round keys, in reverse order. Okay, so now that we understand the DES structure, the only thing that's left to do is specify the function capital F. So let me explain how this function works. So basically it takes as inputs its 32-bit value, let's call it x, but in reality you remember this is R0, R1, R2, R3, and so on and so forth. These are 32-bit values. And then it takes also a 48-bit round key. So here we have our key ki, which happens to be 48 bits. The first thing it does is it goes through an expansion box, And this expansion box basically takes 32 bits and maps them into 48 bits. Now all the expansion box does is just replicate some bits and move other bits around. So for example, bit number 1 of X is replicated into positions 2 and 48 in the output. Bit number 2 of X is positioned in as bit number 3 of the output. And so on and so forth. Just by replicating some of the bits of X, we expand the input into 48 bits. The next thing we do is we compute an XOR with a round key. Sometimes people say that cryptographers only compute XORs. This is an example of that, where, well, we just do XORs in this function. And then comes the magic of DES, where actually these 48 bits are broken into 8 groups of 6 bits. 6, 7, 8. And so let me draw. And then what happens is, so each one of these wires is 6 bits. And then they go into what are called S boxes. And I'll explain the X boxes in just a minute. The X boxes are kind of the smarts of DES, S8. And then the S boxes basically map 6 bits to 4 bits. So the outputs of the S boxes are these 4 bits. They're collected. This gives us 32 bits, right? 8 groups of 4 bits gives us 32 bits. And then finally, this is fed into yet another permutation, which just maps the bits around. So for example, bit number 1 will go to bit number 9, bit number 2 will go to bit number 15, and so on. So it just permutes the 32 bits around, and that's the final 32 bits output of this F function. Okay? So by using different round keys, essentially we get different round functions, and that's how we form the 16 round functions of DES. Now, the only thing that's left to specify are these S boxes. So the S boxes literally are just functions from 6 bits to 4 bits, and they're just implemented as a lookup table, right? So describing a function from 6 bits to 4 bits basically amounts to writing the output of the function on all 2 to the 6 possible inputs. 2 to the 6 is 64, so we just have a table that literally contains 64 values where each value is 4 bits. So here's an example. This happens to be the 5th S box. And you see that this is a table that contains 64 values, right? It's 4 by 16. So 64 values. And for example, if you want to look at the output that corresponds to 0, 1, 1, 0, 1, 1, okay, then you look at these 2 bits. This is 0, 1. And you look at these 4 bits. This is 1, 1, 0, 1. And you see that the output is 1, 0, 0, 1. The 4 bits output 1, 0, 0, 1. Okay, so the S boxes are just implemented as these tables. Now the question is, how are these S boxes chosen? How are these tables actually chosen by the designers of DES? To give you some intuitions for that, let's start with a very bad choice for S boxes. So imagine the S boxes were linear. What do I mean by that? I mean that imagine that these 6-bit inputs literally were just XORed with one another in different ways to produce the 4-bit outputs. Okay, another way of writing that is that we can write the S box as a matrix vector product. So here you have the matrix AI and the vector, the 6-bit vector X. And you can see that if we write this matrix vector product, basically we take the inner product of this vector with the input vector. Remember, these are all bits. So the 6-bit vector, inner product, another 6-bit vector, and we do that modulo 2, you realize basically what we're computing is x2 XOR x3. Right, because only position 2 and position 3 have 1s in it. And similarly, the next inner product will produce x1, x4, x4, XOR x5, and so on and so forth. Okay, so you can literally see that if the S boxes are implemented this way, then all they do is just apply the matrix A